Hi, this is Dr. John Bergduff, and this is the third of our videos on inverses of functions. In the first video, we introduced what we mean by the inverse of a function. In the second video, we talked about how to find the equation of the inverse of a function that is defined by an equation. And in this final video, we're going to look at graphs of functions and their inverses. And we're doing this one a little bit differently because I want you to see me draw some graphs by hand as we go. So, switch cameras here, and we're going to look at graphs of functions and their inverses. Now, in the last video, we actually looked at this particular function, and we determined that its inverse would be given by this equation, going through that four-step process. I want to look at the graphs of these two and just see if there's anything interesting to discover. Now, when I look at this graph, I already know from previous experience that this should be a sideways or horizontal wiggle. Actually, it should be shifted 1 unit to the left from the origin. But I think I would like to graph this one in a more primitive way by just plotting some points, making a table of values of x and y, and seeing what we get from that. Because cube roots can come out sort of unevenly, I want to hopefully be a little bit clever in what I pick. So I'm going to pick the following values for x. I'm going to pick -9. I'm going to pick negative, let's see, -2 and -1 and 0 and 7. And you'll see why I chose those when we actually do some of the calculations here. So if x is equal to -9 and you plug that into the equation, -9 plus 1 is -8, and the cube root of -8 would be -2. Plugging in a -2 into the equation, the cube root of -2 plus 1 would be the cube root of -1, and that would be -1. Plugging in a -1, we'd get the cube root of 0, and that's easy. Plugging in a 0, we get the cube root of 1, and that's 1. And finally, if we plug in a 7, you get the cube root of 8, and that's 2. So you can see why I chose these numbers. Let's plot these points. So -9, -2, 1, 2, 3, 4, 5, 6, 7, 8, 9. -2 would put me right there. -2, -1 puts me right here. -1, 0 puts me right here. 0, 1, and 7, 1, 2, 3, 4, 5, 6, 7, 2 puts me right there. So that's going to create a horizontal wiggle, as you can see, and connecting those points as best I can, it would look something like this. And that is my graph of f. Now, when I graph f inverse, I can use the tools that I know about graphing inverse, about what that function would look like. That's just going to be a vertical wiggle, shifted down by 1. I could use those facts. I could make a brand new table of values, which would be just fine as well, and just create some new values of x and y. But I can also build on the definition of an inverse and realize that once I have the ordered pairs, some ordered pairs for f, I really have some ordered pairs for f inverse too. Because what's the definition of the inverse of the function, of a function? It's a set of ordered pairs formed by reversing the coordinates of the ordered pairs. So if I know some ordered pairs in the function, I can get some ordered pairs in the inverse by simply reversing the x and the y. X becomes y, y becomes x. And I would get these values instead, just literally flipping these ordered pairs around and plotting these points. -2, -9 would put me right about here. -1, -2 would put me right about there. 0, -1 is here. 1, 0 is here. 2, 7, 1, 2, 3, 4, 5, 6, 7 is up here. So those are those points. And you can definitely see you're going to get a wiggle shape here. I'm going to move this just a little bit so I can draw it more carefully. It's going to come up like this, turn through here, turn through here, cross the green graph at one point, and continue on up like that. So that is the graph of F inverse as compared to the graph of F. Now, if I just look at those two graphs as they are, without any other great statements, how those connect together, how those relate together is probably not at all clear. But something really interesting does happen if I add one more feature to this graph. I am going to draw a line through the origin at a 45-degree angle. I'm going to draw that in a different color. Just want to draw that line. And then once I have that line, I want you to look at how the graph of the function and its inverse relate to and compare to this line. So that line goes at a 45-degree angle through the origin. And now you can see it well. Now, if you can't see it exactly as it is here, turn your page just a little bit and notice that the original function, which is the green graph, and the inverse, which is the red graph, are exactly mirror images across that line, or reflections across that line. And now I'm going to put it back in its ordinary orientation, and you can hopefully see that really well. This will actually be typical of graphs of functions and their inverses. This is an interesting line. Let's talk about this line. So if you notice how the line moves from, say, this point right here to this point right here, it goes up 1, over 1, rise of 1, run of 1. That line has a slope of 1. The y-intercept of that line is at the origin. Remember, we use b to represent y-intercepts. And if you think about the slope-intercept form of a line, which is y equal mx plus b from much earlier in the class, if my m is 1 and my b is 0, then that shows me that the equation of that line is y equal x. And this will not be a coincidence. Whenever you draw the graph of a function and its inverse, we will have this mirror image, this reflection property. And this is the summary of what we are observing here. The graph of a function f and its inverse f inverse will always be reflections or mirror images of one another across the line y equal x. Very important. Let's use this to try a couple more examples. As you move along, you're going to discover this technique or this little theorem is very helpful if you have complicated graphs. And here's one that's getting a little bit complicated. You might remember this from the second video as well. This function here is a quadratic function with a restricted domain. And I want to remember what that does. Let's be a little bit more sophisticated in how we draw the graph of f. If you ignore this restricted domain for just a second and look just at the equation itself, notice that it is a quadratic equation, so the graph of f is going to be a parabola. Again, if you ignore the restriction, we'll come back to that. Because of this x minus 2, we remember that the most basic parabola, y equal x squared, would have a vertex at the origin, but this negative 2 shifts you 2 units to the right. And this negative 3 right here is going to shift you 3 units down. So I would have a parabola Shifted, ordinarily the vertex of just the most basic parabola would be at the origin, but we shift 2 units to the right and 3 units down. That puts me right there, okay? And maybe we'll write down what the coordinates of that point are. That would be 2, -3. Now, from there, a parabola would ordinarily have a point 1 unit to the right and 1 unit up from that new vertex. I'm going to do the next one in pencil. You would also ordinarily have a point 1 unit to the left and 1 unit up to create a parabola shape, which I'm tracing just with my hand right now. But the restriction on the domain here tells me to only consider that part of the domain where x is greater than or equal to 2. So we don't look at anything in the graph that would be to the left of x equal 2. So I would not use that point. I would only use points over here. Now, maybe to get the shape just a little bit more precise, and I can see what this point is. Let me write this down. This is clearly 3, -2. But to get maybe a little bit more of a picture of what's going on with f, let's get a couple more values here. We already know that if x is 2, y is -3, and if x is 3, y is -2. We could check this out mathematically. Plug in the 3 here. 3 minus 2 is 1. 1 squared is 1. Minus 3 would be -2. So that's right. Maybe plug in a 4 and a 5 just for good measure and to get a good nice shape here. If x is 4, 4 minus 2 is 2. 2 squared is 4 minus 3 is 1. 4, 1 would put me right there. Like that. And finally, if x is 5, 5 minus 2 is 3. 3 squared is 9. 9 minus 3 is 6. 5, 6, 1, 2, 3, 4, 5, 6 would put me right there. So you can see a parabola shape, but again, it is only going to be half of a parabola, just this half, like so. That's the graph of f. Now again, when I graph f inverse, it is not necessary to make a brand new table of values. You might actually remember, this might help a little bit, that the graph of a square root function is sort of a swoosh. This would be shifted to the left by 3 and up by 2. Let's just see if that's so by looking at taking these ordered pairs and reversing them. So -3, 2, -2, 3, 1, 4, 6, 5. I'm just literally taking the ordered pairs from the original function and reversing them. Plotting those points, -3, 2 would be right here. -2, 3 would be right there. 1, 4 would be right here. I'll label these in a minute. And finally, 6, 5. 1, 2, 3, 4, 5, 6. And 5 puts me right there. Oh, I see I didn't label this one either. So 6, 5, 1, 4, -2, 3, -3, 2. And the point on the green graph that I missed was the point 5, 6. So I'll put that in as well. Now, as I graph these, just as this point right here was sort of a beginning point for the graph of the function, its reflection on the other side will be the beginning point of the graph of the inverse. So it will not continue like this. It will start right here, and you can see a shape developing. And what we're going to do as we're doing this is we're going to try to make it look like the two graphs really are mirror images across that line, and I think they are. You can see the red graph and the green graph are going to cross on their way from 1, 4 to 6, 5. Where they will cross will be exactly on that line. So as best I can, I make it go right through there. And this is the inverse. The two graphs cross exactly on the line. look like mirror images across that line. And again, if it would help to turn this a bit, you can see it even more clearly when you rotate that a bit. Isn't that cool? In a few sections, we're going to be looking at a function called an exponential function and its inverse, which is called a logarithmic function. Don't worry that you don't know those words yet, but their graphs will be mirror images across y equal x. And this will also become very important in trigonometry when you look at inverses of functions there. One final example. Now, suppose that the graph that you're given I don't even give you the equation for it. I just draw you a graph. And here's a really weird wiggly one that I call F. And I am interested in its inverse. Well, basically all we have to do is reverse all the ordered pairs and then attempt to draw something that looks like a mirror image of what we have here. Remembering that the graphs will cross each other. If the graphs cross each other, that will happen on the line y equal x. So let's see if we can make all that work. Let's look at some points that we have. I have the point -9, -5. So in the inverse, I would have the reverse of that, reverse those two, -5, -9. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. -5, -9, right there. In the original graph, I have -4, -1. So in the inverse, I'll have -1, -4. 1, 2, 3, 4, -1, -4. In the graph of the function itself, f, I've got 0, 6. So in the inverse, I'd have to have 6, 0. 1, 2, 3, 4, 5, 6. And look at what happens here. 7, 7, if I reverse that ordered pair 7, 7, I get 7, 7. So it'll be the exact same point on both of those graphs. Now I'm going to attempt to draw something as best I can that looks like a mirror image of this shape. Notice, let's say we start from the left, that from the left, you've got something that does cross this line y equal x. So the inverse will cross, in fact, y equal x at exactly the same point. It will look something like this. Head towards that point. And then to create sort of a mirror image shape, it's going to bow away from the line y equal x towards this one. Again, trying to make this look as much as I can like a mirror image. It's going to blow away and come back towards that point, just doing the best I can. Finally coming up towards the point 7, 7. It will have, notice that the green graph crossed the line y equal x again one last time. I'll have to come in more like that. And is it perfect? Well, I don't know, but basically those look like mirror images of one another across that line. Now, that gives us a pretty good idea of graphs of functions and their inverses. Again, hang on to this idea. You're going to see it again. And this is our final video on inverses of functions.